In this lecture, we'll talk about one good property of the OLS estimator, which is the consistency of the estimator. Let's first review what we have done so far. In lecture 1, we introduced this linear regression equation right here. Written in vector form, it's shorter in this way. So it's written in vector form, it equals this, equals x vector prime beta vector plus u. In lecture 1, we emphasize the interpretation of this observable part as well as the interpretation for the beta parameters depend on your research purpose and depends on the assumptions that you put on the model. So we talked about the descriptive research purpose. So when the purpose is descriptive, we treat this as a descriptive equation. So this may be the conditional mean of y given x, or this may be the projection of y on the space of x1 to xk. And if the purpose is causality, then we give a model. We give a story to this equation. We say that y is generated from the random variables x and the u in this form, and in that case, the betas can be interpreted as the causal effect of the x variables. Now, all those interpretations are based on the true values, the true population values of the betas. And those values are unknown. The true values of the parameter are unknown. And in lecture 2, we introduced an estimator for this true value of the parameter vector. And that estimator is based on a sample of size n. And that estimator is the ordinary least square estimator, which is defined to be the minimizer of the least square criterion function. And we introduced some matrix algebra to help us to solve for an explicit form for the estimator. Written in vector form, the least square criterion function is like this. And if we solve this minimization problem, we get the formula for the ordinary least square estimator, which is this. It is the inverse of sum of x vector times x vector prime times the sum of x vector times y. So that is the explicit formula for the ordinary least square estimator. And at the end of last lecture, I said that whether this estimator is any good, does it have any good, whether it has any good property depends on the model assumptions. And when we talk about good properties of the estimator, we are viewing this estimator as a vector of random variables, or in other words, a random vector, because it is a function of the random sample, which is a collection of random variables. And this is this way, so this sample is treated as a collection of random variables because we take the ex ante point of view when we study the properties of the estimator. So we talked about ex ante and ex post point of view extensively in the first part of the course, but now let's quickly go through it again. Ex ante point of view is before the sample is drawn. So before the sample is drawn, we don't know what the, so this is the population of Hello Kitties. Before the sample is drawn, we don't know whether the sample is this one or a different one or even a different one, right? So before the sample is drawn, we do not know what the sample is. And from that point of view, the sample is a random thing. And from the ex ante point of view, the sample is random. Contrary to that, there is this ex post point of view. That is the point of view after the sample is drawn and observed. So after the sample is drawn, we observe, let's say the sample is this one, and we observe a bunch of numbers for these Hello Kitties. From the ex post point of view, the sample is already given, is known, is fixed, is a set of numbers. And why do we take the ex ante point of view instead of the ex post point of view when we evaluate the properties of the estimator? So the reason is, as we said before, ex post is not very useful for judging the quality of estimators. So for example, suppose that ex post your sample is drawn and observed to be this table, your sample of individuals for which you observe their wage, their gender, and their experience. Let's say after the sample is drawn, you observe this table. Then you can calculate your ordinary least square estimator, say of wage regressed on female and experience. And you can calculate that based on this sample. And plugging in the numbers from this sample, you can get the numerical value of the estimator. Let's suppose it is 6 minus 2.7 and 0.07. This is a numerical value. But how far is this numerical value from the true value of the parameter that you want to estimate? Well, you have no idea, because this is a fixed value and that is a fixed value that is unknown. So you have no idea how far this is from the true value. So exposed, you're comparing a fixed numerical value with something unknown. You have no idea how far they are from each other, and that is not a very useful point of view to evaluate how good an estimator is. On the other hand, ex ante, the sample is still random, and the estimator is also random. And for a random variable, we can calculate its probability limit. We can calculate its expectation, its variance, and probability limit, and compare those with the true value. We can compare the expectation or the probability limit with the true value. And those comparisons will give us information about how the estimator behaves. So, and those information can tell us about whether the estimator is consistent or unbiased. But today we're going to focus on consistency, right? So up and down are part of an estimator, but the key to success is consistency. So what is consistency? We have learned about consistency already in the first part of the course, but just to review, the estimator is consistent for the parameter that you're estimating if and only if the estimator converges in probability to the parameter, the target parameter value, as the sample size diverges to infinity. So what that means is, as long as you collect more and more data, as long as your sample size grows, your estimator will approach the true parameter value you're estimating. If you can collect an infinite sample, then your estimator will be equal to the true parameter value. So that's the idea of consistent estimators. And in the first part of the course, we focused on a scalar estimator for a scalar parameter. Now we have a vector estimator for a vector parameter. Then what does convergence for the vector means? So that simply means the convergence of each element of the vector. So that basically means beta hat 0 converges in probability to beta 0, beta 1 hat converges in probability to beta 1, and beta k hat converges in probability to beta k. So that's basically what this convergence of this sequence of random vectors means. All right, so that's the definition of consistency. We already introduced this notation in the first part of the course, so I will not spend too much time on this now. And the convergence in probability means, just to review that, it means the probability that the estimator is in a small interval around the true parameter value converges to 1 as n go to infinity. So graphically, we can demonstrate how an estimator converges in distribution to a parameter. Now, in this graph, we are plotting the probability density function of this estimation error. So this estimation error goes to 0 in probability as n goes to infinity, and we can check different n's and see how it happens, right? So this is the probability density of this estimation error at a relatively small n equals 20. And let's say this is your small interval that you choose to evaluate it at. So that's minus epsilon plus epsilon. Then at this smaller sample size, there is pretty big probability that the estimation error is beyond epsilon. Right? The probability that it's within epsilon is relatively small. It's relatively far from being 1. But let's see what happens when you increase the sample size to 100. When you increase the sample size to 100, then the relative area of this part within minus epsilon and epsilon is bigger, it's much bigger than on the previous graph. Now, if you increase the sample size even bigger to 1,000, then almost all the time, the estimation error is in between minus epsilon and epsilon. Right? The probability that the estimation error is beyond epsilon now is quite small. And if you increase the sample size even more, you can expect this trend to continue. So that's what consistency means. Now let's focus on the ordinary least square estimator. So we estimate the beta vector in this linear regression equation using the ordinary least square estimator. Is this estimator a consistent estimator? So we want it to be consistent. Is it consistent? Whether it is consistent or not depends on model assumptions. So that's why I say here, yes, it is consistent, but we need assumptions to guarantee consistency. Without those assumptions, we cannot say that it is consistent. So now let's talk about assumptions. What are the assumptions that we need for the consistency of the ordinary least square estimator? Basically, there are 4 assumptions here. The first assumption is orthogonality. Second assumption is Iid sample. Third is unlikely large outliers. And 4 is no perfect multiculinarity. Let's explain each of them. Let's first define each of them and then explain them one by one. Now, so what is orthogonality? Orthogonality, written in mathematics, means that the error term u has expectation 0 and it's orthogonal to all of the included x variables. Orthogonal meaning that it has 0 correlation with these x variables. Okay, so this is the mathematics of the orthogonality condition. So in words, it says that the error term has expectation 0 and it's uncorrelated with the covariates. Why do we need this assumption? Well, recall that the sample residual, okay, the residual, the yi minus the linear function with beta hat in it, not beta hat prime xi vector. The residual, the ordinary least square residual, automatically by definition satisfies that the sample average of it equals 0 and the sample correlation of it with any of the x also equals 0. So the regression residual is yi minus beta hat times xi vector, and the error term, remember, is quite analogous to that, is yi minus beta vector prime xi vector. Now, if we want this to be close to that, it's reasonable to believe that those properties are also holding in population for the UI. Okay, so that is one reason that we need these assumptions, these orthogonality conditions. Well, the ultimate reason is that we're going to need this when we prove the consistency. But intuitively, you can understand that this is just to create an analogy between the population quantity and the sample quantity. The sample correlations are always zeros. So one reason is to match the sample features of the regression residual. Well, and another big question is it a reasonable assumption? So now that we already know that we need it, but is it a reasonable assumption? Can we expect it to hold in practice? The answer to that is going to depend on the assumption. The answer to that is going to depend on the model that we are studying, okay, the research purpose. So the orthogonality condition, the first equation in the orthogonality condition is that U has expectation 0. This is typically viewed as a normalization because we have an intersect in this equation. So if EU is not 0, we can lump EU with the beta 0, the intercept, and create a new error term that does have expected value 0 that typically doesn't affect anything. So EU equals 0 is typically just a normalization, so it's not restrictive, but we lump it in the orthogonality condition for simplicity. But the rest of the orthogonality conditions are more substantive. So these are more substantive. Whether they hold or not depend on the context. Now, if your research purpose is descriptive, if you have a descriptive model, and let's say you do not assume that your conditional mean of y given x are linear, then this linear regression equation can describe a projection model. Is a projection model. It describes the projection of y on x. Projection of y on x is given by this observable part of the equation. In this context, the purpose is descriptive, and you treat this linear part as the projection of y on x, then the error term equals y minus projection of y given x1 to xk. Then orthogonality automatically satisfied is automatically satisfied. So if this observable part is treated as the projection of y on x1 to xk, and u treated as the difference between y and the projection, then orthogonality condition automatically satisfied. And this was proved in lecture 1. So if you don't remember, you can go back to lecture 1 and have a look. So in projection model, orthogonality condition is by definition satisfied. Now, on the other hand, if you assume that the conditional mean is linear, and you use this part to describe the conditional mean of y given x, then u is the difference between y and the conditional mean. In this case, orthogonality condition is also automatically satisfied. The reason is when conditional mean is linear, conditional mean equals projection. So in other words, when conditional mean is linear, this is a conditional mean model, but at the same time is also a projection model. So therefore, for a conditional mean model, the orthogonality condition also is automatically satisfied. Now, it's a much different story in the causal model. It's not so easy to guarantee the orthogonality condition in a causal model. Okay. In a causal model, remember, we need to tell a story about how y is generated, how y is determined by x and the unobservables. And in that story, the unobservable, the error term, is a summary of all the factors excluded from the equation, but participate in the generation of y. So U summarizes all the excluded factors, right? Factors excluded from our linear regression equation, but may be relevant for how y is determined. So U is a summary of all the excluded factors. And those factors have real economic meaning, and there is no guarantees that these factors are uncorrelated with the x variables. Whether we can reasonably say that those factors are uncorrelated with the x variables depends very much on the population from which the sample is drawn. It depends on how the data was generated. Now, to fix ideas, we can consider an example. In this example, we let y be log of wage and let x1 say there is only one x variable, which is years of schooling. Then clearly in the determination of wage, education is an important factor, but there are also other factors. So in our story, we say that education determines a person's productivity and therefore determines a person's wage, but many other things also determine the productivity and also determine the wage, and therefore also determine the wage. So in this causal model, beta 1 is the return to education, but can you say that the orthogonality condition is satisfied in this causal model? Can you say that the schooling is uncorrelated with the other factors that also determine the wage? Suppose that your population, so data are randomly drawn from the population, and the population is the population of adult male in the United States, then can you say that this factor, these omitted factors, is uncorrelated with education? Well, if you know anything about the education system of the United States, you probably will say, not really. For example, um, let's say that an important factor in U, in the error term, is IQ. So IQ is the main suspect in the wage determining equation, right? So the intelligence of the person clearly affects the productivity, and clearly it's part of the determining factors of Y. And if you know anything about the education system in the United States, you know education are chosen by individuals out of their own free will. And also it's a result of the matching between the schools and the individual, right? So um, there are many reasons to believe that IQ is highly correlated with education. As students who have higher IQ find schooling easier and therefore they go on for more years. And students have higher IQ are also more likely to be admitted to um, college or postgraduate study, and therefore they obtain more education as well. So there are many reasons to believe IQ is highly correlated with education. And therefore, there are many reasons to say that the orthogonality condition does not hold. So the orthogonality condition is unlikely to hold in this situation. But now let's consider a different data set. Okay, let's say the data set comes from a crazy kingdom called RCT. In this crazy kingdom, education is not individual choice, but rather is randomly assigned. And once assigned, it's strictly enforced. So the king randomly assign education level to every uh, constituent, to every subject of the kingdom. And once the number is assigned, that person is forced to go through that many years of education. And suppose all other aspects of life in that kingdom is the same as in the United States. So wages still determined by productivity, education still affects productivity, and IQ still affect activity. So the causal equation is still the same. But now, because education is randomly assigned, regardless of a person's IQ, now in this fake data set, you can reasonably say that X1 and U are not correlated. Okay, so U might still contain IQ, but in this crazy kingdom, education is randomly assigned. And now it's reasonable to say they're orthogonal. Okay, so in that population, orthogonality condition does seem to be reasonable. Now, so that is the orthogonality condition. And the second assumption we made is the IID assumption, IID sampling assumption. This assumption basically says that this random vector are independent across I. So across individual, the random variables are independent. Okay. And also, we say that they are identically distributed. That is identically distributed means that it follows the same distribution, follows the distribution of the population random variables. And we need this. So why do we need this? We need the independence part as well as the IID part because we want to use the law of large number to derive consistency. And we have only covered law of large number for IID samples. We do not have other law of large numbers at this point. Okay, so that's why we assume IID. In general, if you want to ask whether we can relax this assumption in general, yes, we can relax this assumption, but we're going to need some other law of large numbers. But for now, let's assume IID assumption. Okay. So the second question is whether this is a reasonable assumption. Does it hold in practice? It is, in fact, a reasonable assumption in a lot of cases. If the sample is randomly drawn from a large population, it's a randomly drawn subset of a large population, then the IID sampling is quite reasonable. Such samples are common, so a lot of data sets are randomly drawn subsets of a large population. But I also want to say that other sampling schemes exist and are actually very common as well. For example, time series data, in which the data are composed of observations for one entity, one individual, or one country over different time periods. So that is not a random sampling environment, and the data you got is not IID sample. Or you could have a panel data where many individuals are observed, but also over multiple time periods. Then the observations across time periods are in general not independent from each other. There are other ways of sampling that could also violate the IID sampling assumption. For example, convenience sampling. So if a child is drawn to be included in a sample, his or her sibling are also included because it's just easier to interview all the kids in one household. But that can create dependence between the observations. So under these different sampling schemes, the data for different I may be dependent and the IID sampling assumption may be violated. But for now, let's not worry about that. Let's assume that IID sampling does hold, and our data set is a randomly drawn subset from a very large population. Now, the third assumption is about how likely large outliers are. So we assume that large outliers are not very likely. So what does that mean in mathematics? That actually means the finiteness of the fourth moment of all the variables, of the x variables and of the y variable. So the x variables and the y variables are assumed to have finite fourth moment. Well, you might have many questions at this point. How do we understand this? How is finiteness of the fourth moment related to outliers? And why do we need the outliers to be unlikely? So the fourth moment is can be viewed as a kurtosis. So kurtosis is not exactly the fourth moment, but when the fourth moments are finite, the kurtoses are also finite. You can look up the definition of kurtosis, which is not very important. It's just the way that we refer to the fourth moment. So how is the kurtosis related to large outliers? Now, let's draw some pictures and get some intuitive idea from the pictures. First, I'm drawing a distribution with finite kurtosis. So this is the probability density function of the standard normal distribution. Standard normal distribution has finite fourth moment, finite kurtosis. So this is the PDF of that distribution. You can see that the probability that a standard normal random variable takes values say between -4 and 4 is very high, the probability that it takes higher values is still positive, but the probability gets very, very low when you are beyond a certain number. So the probability dies out very quickly as you go away from the center of the distribution. And it goes away, so it diminishes so the probability diminishes very slowly, very fast. That fact determines, that facts tells us that the kurtosis of the distribution is finite. Now let's compare that with a distribution without finite kurtosis that doesn't satisfy this assumption. And this probability density function is drawn in blue, and that's the probability density function for a student t distribution with 1 degree of freedom. So don't worry about what that is. It's not important. It's just a distribution that's different from the standard normal, but the probability that so the density dies out much slower than the standard normal as you get away from the center. The fact that the density dies out much slower determines that the probability that this random variable, the random variable following the T1 distribution, takes very large values is higher than the standard normal random variable. And because it can take very high values with not too small probability, the fourth moment of that distribution is infinite. Okay, so that distribution has infinite kurtosis. Infinite kurtosis means the random variable following that distribution is more likely to take large values than the standard normal, than one with a finite kurtosis. And the large values that are really, really large, so large that it seems to be an outlier from the typical values, those values are considered to be the outlier. Okay, it's easier to visualize by this. Visualize the outlier from this scatter plot. So here I'm comparing two scatter plots. The scatter plots of X and of a data that contains X and Y pairs. And that the graph, the scatter plot on the left is the scatter plot of a data set of 100 people drawn from this generation process. So for those 100 people, yi equals xi plus ui, where ui follows a standard normal distribution. Here I believe I let x and y, I believe I also let x to follow a standard normal distribution as well. So x is also follows standard normal distribution, and u also follows standard normal distribution. So y will also be a normal distribution. In that case, if I draw a sample of size 100 from that data generating process from that population, I typically get a sample that looks like this. Say the maximum value for x, maximum value for y, and the minimum value for x, minimum value for y, they are not very extreme. Like y runs from -4 to 5, x runs from -4 to 4. So they're not very extreme, and the points are kind of clustered together. It's not that y or x cannot take huge values. The probability that y can take value greater than, say, 100 is still positive, right? Because the support of the north standard normal is the whole real line. It includes every point on the real line. So it is with positive probability. So the probability that y can take very large values is still positive, but it's so small that when you are drawing a sample, it's very unlikely that you get any point beyond a large number. And typically you get something like this. Typically you get a sample where the points are relatively clustered around each other. But on the other hand, if you so you keep the distribution of x to be still standard normal, but if you change the distribution of ui to T1, which doesn't have finite kurtosis, then you draw the sample again, you draw a sample of size 100 again, then very, very likely you're going to get a sample that looks like this, which is quite different from the one from the previous one, the one on the left. So what's so different about this graph? What's so different is this outlier point. That point is so far away from the majority of the point. At that point, the value of y is almost 100. Okay, so that is an outlier. And it is in fact quite often that you get a sample with one or more outliers when U is from a distribution without finite kurtosis. Okay, so that's how the finite kurtosis is related to outliers in a data set. All right, so that explains what this assumption is. But why do we need this assumption? We need this assumption for a mathematical reason. That is, our law of large number requires it. Our law of large number, remember, requires the variance of the relevant random variable to be finite. And you will see that we are going to apply the law of large number on, actually not on u or on x, but on x times u. If we want the variance of that to be finite, you need the fourth moment of x and fourth moment of u to be finite. Okay, so that's a mathematical reason that we need the finite kurtosis assumption. We need the large outliers to be unlikely. There is also an intuitive reason, which is that the large outlier distorts the regression line too much, and getting large sample size will not help us to correct that distortion effect, because getting larger sample size simply means that you're getting more and more outliers, and your regression line is always distorted. So those are the reasons that we need this finite kurtosis assumption. But what does it mean in practice? Is it satisfied in practice? Well, in fact, this is not an assumption that we worry too much in practice. The reason is most economic variables are believed to be bounded. If they're bounded, they do not take huge values. There is a maximum to the value that they take, and the random variable, therefore, can always have finite kurtosis. For example, education. You cannot have like 100 or 1,000 years of education. That doesn't happen. So for those bounded random variables, we do not worry about this assumption at all. And there are some variables that can take large extreme values, like income. In those cases, we often take a logarithm of the random variable before putting it in the regression equation. Taking a logarithm will change the scale of the random variable so much that the logarithm of the random variable can often be something that have a finite kurtosis. And sometimes outliers in the data set indicates an error in that entry, and we should probably try to correct that error before using that outlier in our data set. Okay, so for example, if in your data set you find a 91-year-old college student, that's probably wrong, and you might want to drop that observation. All right, so in practice, the bottom line is that in practice, we don't worry about this assumption very much. Now, the fourth assumption is no perfect multicollinearity. So no perfect multicollinearity. So what is the no perfect multicollinearity assumption? The statement of the assumption is that there is no x variable that is a perfect linear combination of other x variables. Written mathematically, there is a mathematical way to write it, which is expected value of the x vector times x vector transpose. Recall that this is a matrix. It's a k by 1 by k by 1 matrix. That matrix is invertible. So this verbal statement and this mathematical statement, they are the same. They mean the same thing. Okay, so no x variable is a perfect linear combination of the other x variables. If that is the case, then expected value of this matrix is invertible and vice versa. So that is what the fourth assumption is. Why do we need it? Suppose that this assumption doesn't hold, we run into a very serious issue. So let's see what serious issue we run into. Suppose that this assumption doesn't hold. That means there is an x variable that is a perfect linear combination of the other random variables. So what that means is suppose that that random variable without loss of generality, that's suppose the first random variable, the first x variable, is a perfect linear combination of the other random variables. What that means is there exist some numbers, some coefficients, such that the first random variable equals this linear function of the other random variables. Exactly equal. That is, this exact equal means this it is a perfect linear combination of the other x variables. Okay. So let's say the first x variable is exactly equal to this linear function of the other random variables. So that's a realization of no perfect multicollinearity assumption. Now for this equation, we can rewrite it in a different way. We move everything to one side of the equation. So that becomes a0 minus x1i plus sum aj xji. So these a's are constants. So this means that there is a linear combination of all the x variables that equals 0. We can write this in a vector form. We collect all the coefficients and we collect all the x variables and write them as the inner product of the coefficient vector and the x vector. So we can write it in another way. That is, we can define, so let me write it here. We can define the a vector to be this column vector of a0, which is a coefficient of 1, and minus 1, which is the coefficient on x1i, and a2 to ak. We define a vector to be this, and remember the x vector is 1 x1i to xki. Then the left hand side of this equation, that equals a vector transpose xi vector, the inner product of the a vector and the x vector. Right, so that inner product equals a0 times 1 plus minus 1 times x1i plus a2 times x2i plus ak times xki. So that's exactly the left hand side of this equation. So violating the no perfect multiculinarity assumption means that there is a non-random vector A such that A prime xi equals 0. So A prime xi equals 0 for all I. Okay, because x1 is a linear combination of the other x for all I. Okay, for all realizations of the x variables. If that holds for all I, then this matrix product, so A prime sum of xi prime times A, this matrix product can be written as sum I from 1 to n. So this A vector can be moved inside of the summation. It is a constant relative to I. So that's the sum of A prime xi prime A, right? Now we can look at this thing that we're summing up. A prime x, that is an inner product of two column vectors. Inner products are scalars, so that is a scalar. This is also a scalar. So that is a scalar. It equals the sum of the products of the corresponding elements of A and X. And this is actually the same thing because this is also the inner product of the same two random vectors. So they are actually equal. They are the same scalar. So that equals A vector prime xi squared. For generic A, because this is sum of something squared, this is always non-negative. So that shows this matrix in the middle, this pink matrix in the middle, is always non-negative for whatever A vector you put here. So what does that mean? That means this pink matrix is positive semi-definite. Is positive semi-definite. But now, if we let A be that A vector that we just chose, that satisfies A prime xi equals 0, then we make this matrix product exactly 0. So that means but this is 0 for the for the A vector defined above. So this is non-negative for any A, and it is 0 for this A, and this A is not a zero vector, okay, because it's got at least one non-zero element. What that says is this matrix is positive semi-definite, but not positive definite. So that means this is not positive definite. So a positive semi-definite matrix that is not positive definite is what? Is not invertible. So that matrix is not invertible. But remember, what's the definition of the ordinary least square estimator? It is this. It involves the inverse of that pink matrix. If it is not invertible, then the inverse doesn't exist, then the ordinary least square estimator doesn't exist. It's not well defined. Okay, so that's the serious problem that we run into when we have perfect multicollinearity. Now we can consider an example where this could happen. This is a typical perfect multicollinearity example. I should always emphasize it's perfect multicollinearity. This is an example of perfect multicollinearity. What's the example? In this example, the x variables contain f and m, where f is a binary variable, is a dummy variable, indicating female. So f equals 1 if the person is female and 0 otherwise. And m is the dummy variable indicating male. So m equals 1 if the individual is male and 0 otherwise. And suppose there are only two genders, either the individual is female or the individual is male, then f plus m is always 1. So whenever f is 1, m is 0. Whenever f is 0, m is 1. So f plus m equals 1. So there is a perfect linear relationship between these two random variables. This is an example of what we call the dummy variable trap. That is, if you have a categorical variable and you create a dummy variable for each and every category, then including the dummy variables for all categories in a linear regression will cause perfect multicollinearity. It's like now gender has two categories and you can create two dummy variables, but if you try to include both dummy variables in your linear regression, you have a perfect multicollinearity problem. Solution is very simple. You simply drop one of the dummy variables, or you could drop the intercept. You could drop this one too. Which one to drop depends on depends on what question you want to answer with your regression equation. Now, we say that perfect multicollinearity causes a serious problem, but that doesn't mean that we cannot have correlated x variables in a regression equation. The x variables can be correlated. The point of multiple regression is to include correlated x variables, okay? So that we can separate the effect of different but correlated random variables. So we can allow correlation. We can even allow highly correlated random variables in X. And even highly correlated random variables is not a problem on its own, as long as it's not perfect. But highly correlated random variables, highly correlated X variables when combined with small sample size, can mean that you cannot precisely estimate some of the coefficients. Now, I want to give you an example, continuing the gender example as before. Suppose now your data set is collected with progressive thoughts. Gender is not binary. Suppose gender is not binary, so Fi plus Mi is not exactly 1 for all I. There might be individuals who are not willing to be identified as either F or M. In that case, you do not have perfect multiculinarity. So Fi plus Mi equals 1 doesn't hold exactly. As a result, however, people who are not willing to identify either F or M is a small minority. So there are non-binary individuals out there, but there are very few of them. As a result, say you have a data set that contains 1,000 individuals. In your 1,000 data set, in your data set of 1,000 individuals, you have only 2 who are non-binary, for whom Fi plus Mi is not 1, but 0. In that case, you can still run the ordinary least square regression. You can still calculate the ordinary least square estimator. However, you won't be able to estimate beta 0 very accurately. Why beta 0? The reason is beta 0 is the expected Y for those who are neither female or male. So beta 0 is the expected Y. So under the first assumption that EU given F and M given gender equals 0, so under A1, EY given that the person is non-binary, not female or male, equals beta 0. So beta 0 is the expected Y for those who are non-binary, but you have only 2 individuals who are non-binary in your data set. With a sample size of 2, you are not able to estimate this expectation very precisely. Okay, so high correlation is not a problem per se, but when you combine that with a relatively small sample size, you can run into this problem that you cannot estimate some of the parameters precisely. This does not mean that your estimator is inconsistent. The ordinary least square estimator is still consistent even when your X variables are highly correlated. It simply means that you need a larger sample size than n equals 1,000. Say maybe you want a sample size of n equals 100,000. Or maybe you want to use some other sampling schemes that will give you more non-binary observations in the data set. So that's the discussion of the fourth assumption. Now, let's try to prove the consistency of the ordinary least square estimator. Just to sum up the assumptions that we introduced, we want the error term to be orthogonal to the vector 1 and to all the x variables. So the error term should have expectation 0 and should have 0 correlation with any of the x variables. And we want the sample to be an IID sample. And we want finite kurtosis or unlikely large outlier. And we want no perfect multiculinarity, which implies that this matrix is invertible. Okay, so Now let's try to prove the consistency of the ordinary least square estimators under these four assumptions. To do that, we start with the explicit formula that we derived in last lecture for the ordinary least square estimator, which is this. The first thing we do is that we're going to multiply 1 over n to this summation and also multiply 1 over n to the summation inside the bracket. Doing that will not change the value because this 1 over n is multiplied to something that's inside the inverse. So what we are actually doing is multiplying n, right? And if we multiply n and then divide by n, the value of the expression doesn't change. So beta can be written as this form. That's the sample average of this random matrix inverse times the sample average of this random vector. The next thing we do is to remember that y is equal to this linear function of x plus ui. So that is the linear regression equation we started with. Remember, that's the linear regression equation we started with. Now we're going to plug that in this formula. Replace yi by this formula. So we replace this yi by that formula. We get here, we get this. The next step is to distribute this x vector to these two terms in the parentheses. So this product becomes xi prime beta plus xi times ui. Right? So that becomes xi prime beta plus xi ui. Now that's the sum of this sum. The sum of this sum is a very long sum. We can collect all the terms with the xi prime beta and write them together. That is the sum of xi prime beta. And we can collect all the terms with xu and put them in this summation. So that becomes the summation of xui. And therefore that can be written as this pink matrix inverse times this sum of x prime beta, and this pink matrix inverse times the sum of xui. Now let's focus on this first assignment, this term. For this term, as you can see, the beta vector doesn't have a subscript I, so it can be factored out of the whole summation or average. It can be factored out, but because it was on the left before, once you factor it out, you still keep it on the left. Sorry, on the right, not on the left. But now once you factor that out, you see this matrix is actually equal to the matrix inside the inverse. So that's the matrix inverse times the matrix itself. By the definition of inverse, these two cancel out, and you get an identity matrix. The product of these two is the identity matrix. An identity matrix times beta equals beta. So this term becomes beta. Now I'm not doing anything about this term. I just copy it and write it here. So beta hat becomes beta plus this estimation error. Now let's move on to the next page. So beta hat equals beta plus the estimation error, which is written in this way. Now, as you can see, beta hat minus beta is in fact a function of this random matrix and this random vector. Now, if we define a function little g of a matrix Q and a vector R to be Q inverse R, then this estimation error beta hat minus beta will be G of sample average of x prime and sample average of xu. So that is our Qn matrix, and that is our Rn vector. Right? So the reason we do that is we want to use the Slavsky theorem. We talked about one version of the Slavsky theorem, and here this is another version, which is basically the same as before, just in a different notation. To introduce the Slavsky theorem, you consider a sequence of random matrices, Qn, and a sequence of random vectors, Rn, and also consider a function g of Q and R. Suppose that each of the sequence converge in probability, so the random matrix converges in probability to a non-random matrix Q0, and the random vector converges to a non-random vector R0. And also suppose the function g is continuous at this limiting point. Then the function g preserves convergence in probability. Okay, so that's the Slavsky theorem, which simply says continuous function preserves convergence in probability. Now, you might be wondering what we mean by a random matrix sequence converges to a matrix. Well, that we simply means that each element of the matrix of Qn converges to the corresponding element of Q0. All right, so that's the vector version of the Slavsky theorem, and we can use that next. But before using that, we notice that this is our Qn, and this is our Rn, and G is a continuous function except at points where Q is not invertible, right? At any point where Q is invertible, it is a continuous function. So we want to use the Slavsky theorem. In order to apply the Slavsky theorem, we want to show that this Qn converges in probability to something, this Rn converges in probability to something, and we want to also make sure that the probability limit of the Qn is an invertible matrix, so that it's on the continuous part of the G function. All right, so next we will work on the Qn. So this is actually our Qn. Qn matrix. And this is actually the Rn vector. The Qn matrix converges in probability to this Q0 matrix. The reason is every element of this sequence is a sample average of an Iid random variable. So for example, the first element is 1 over n, sum I from 1 to n. So this is actually not the first element. The first element is 1. But that one is trivial. We can consider the second diagonal element, which is 1i times 1i. And because the x1i's are independent and identically distributed, the x1i times x1i is also independent and identically distributed across I. So if you treat that as a random variable, and across I is IID, you can apply the law of large number and shows that this converges in probability to expected value of x1i, x1i. So that's by the law of large number that we have covered before. You apply that to every element of this matrix, and you are able to show that this random matrix sequence converges to this non-random matrix. Same thing happens here. You can apply the law of large number for this for this sample average of this random vector and show that this converges in probability to expected value of the random vector. So that is the limit R0. Now, I want to show that this R0 is actually 0. And that actually follows from the orthogonality condition. The reason that it follows is that this Ex vector U equals E of 1x1 to xk times U, where U is a scalar. So that is actually U x1U xku. And expectation of a random vector equals the vector formed by the expectation of each element. And that is 0. Each element is 0 by A1, by the orthogonality assumption. So this R is actually 0. Now we are ready to apply the Slavsky theorem. We can apply the Slavsky theorem also because this matrix is invertible by the non-perfect multiculinarity assumption. And therefore G of QR is continuous at this limiting point. So we can apply the we can apply the Slavsky theorem and show that beta hat equals beta plus G of Qn Rn converges to beta hat, converges to beta plus G of Q0 R0. And G of Q0 R0 is the Q0 inverse times R0, but R0 is 0. So therefore, the limit of the ordinary least square estimator is the true value.